So yes, this is going to be recorded. And the agenda is that I thought we would do some administrative questions. So anyone who has an administrative question kind of about the exam before we get into the particular math stuff, now would be an excellent time. If you would please primarily post your questions in the Q&A. I will not be looking in the chat so much. So the Q&A is really where I'm going to be going for looking for and answering questions. So make sure you post them in there if you would like me to actually talk about it. What was I going to say? Oh yeah, so administrative stuff. Then I downloaded exam that I looked at what was reviewed in the classes today and also what the D2L practice exam is all about. And it looks like really maybe these weren't covered so much. And so I thought maybe these are some problems that, could be interesting for everyone. And so we'll go over some of these after the administrative questions, and then it'll just be kind of an open free-for-all sort of deal. We got the upvoting on here. So if multiple people have the same question, try to get a question upvoted, and then kind of the highest ones appear higher on my screen. And those are the ones that I'm going to be addressing first. Will there be any change of variable problems, aka anything from WebWork 23? So you saw a little bit on the quiz how we can make these reasonable. So the full style questions obviously take a long time, but we can ask how a particular piece of a boundary is transformed under some transformation T, maybe like was on the quiz, and then also some like true false sort of stuff. So that's it's possible that there could be a full problem, but I think the time needed in order to actually do that is quite long. So I mean, a good chunk would have to be dedicated to that. Basically, how we time the exams, what we're looking for is that when an instructor or someone goes and takes the exam after it's been written everything, we're looking for about a 1/3 factor. So these are meant to be 60-minute exams. So if we take the exam and we can complete it in 20 minutes rather comfortably, that's kind of in general what we are looking for. Will they be a curve at the end of the class? So we always look at the grade distributions at the end of the class. And I mean, I can't say that there definitely will be. I can't say that there definitely won't be. We have to look at the grade distributions and kind of compare them to previous semester's grade distributions, and then that will ultimately determine it. Will the final exam cover everything or just the stuff between exam 3 and the final? It is cumulative, the final exam, so it will cover everything. I suspect that there'll be a little bit more emphasis placed on the things post-exam 3. What is the exam format? Like number of questions and how many multiple choice true false. So there are 6 standard response questions, 4 multiple choice questions, and 4 true and false questions. I would be very surprised if that changed at this point. But yeah, so that will almost certainly be the distribution. How long do we have to turn in our work after the exam? The standard 15 minutes. So try to stay as close to that as possible. So long as it's some reasonable time frame. And I mean, if it's 17 minutes, don't sweat or anything like that. But if it's several hours or whatnot, maybe you should email me or one of the instructors and just let them know why this happened. Just give us a heads up. Let's see. I do my math 24 on their due dates. For this reason, I've not been able to complete homework set 27. Full credit. So we are not pushing the due date back for homework 27. This is interesting. It's the first I've heard of this, but there was a decent push to move it to Wednesday. So that way kind of it helped motivate folks to keep up and make sure, because really on Thursday, you should be, if doing anything, you should be studying for the exam. And so I think that's kind of, folks just wanted a little extra push in order to get that done so that way they could focus on the exam. So that's what we're trying for exam 3. Of course, for the final exam, I don't know, I guess I have to look. I think there's a day of review and whatnot. So yeah, I'll have to look and see what's happening for the final exam. But again, we kind of changed this because of suggestions from the students. We moved it from the due on Thursday to due on Wednesday. And so if there's a push, back to, again, I don't know what the final exam, when that due date is. I would suspect that it's on like Sunday or something, but I'd have to check. But let us know what you think. If we want to argue for partial credit on an exam, who do we go to? So yeah, in the syllabus, there's a instructor who's in charge of partial credit. And so that's who you should, I suppose, send emails to. He's the right person who could overrule the TAs and whatnot, or whoever graded your exam. Is this semester showing a lower average grades in your experience? So no, actually it's showing a higher than in previous semesters. The grades have been higher overall with this new format. There's a lot more leniencies built in. I mean, before we never had attendance categories, we never had participation, we never added to homework, all that sort of stuff. And so I think that's probably what's contributing a fair amount to this. How many questions will be on the exam? I think, yeah, you guys answering this for me. I don't need to reiterate that. Yep, 14 questions is what we're at. And I already mentioned the breakdown. And again, so we're recording this. I'm going to post this. If you miss anything, you can go back and take a look. Should I be concerned about getting 80 minutes on the exam as opposed to 60 minutes? Also, the exam is only over double and triple integration, right? I'm not sure what you mean by concerned. We use the same measure that we did for exam 2 and exam 1 in order to determine if the length was decently appropriate. For whatever reason, it did not work great on exam 2, as many people told us. And so that's why we added the 20 minutes. But still, we timed it, and it's intended to be a 60-minute exam, and we're giving more time for that. So we did not add more questions because it's an 80-minute exam. That's supposed to be time for you to go back and check your work, carefully enter things into the calculator, things like this. Yes, we're going to do an exam 3 review. This is, yeah, so this is from a previous exam. The distribution was different, right? Back then, there was only 2 exams that were each 90 minutes long. Here we have 3 exams that are 60 minutes long. So yes. What's the best way to what's the best way to study for true and false? I struggle the most with those. That's a good question. And those ones are very, by and large conceptual. And so you really have to have a good understanding of the material typically in order to get those. The things that I would say that you should definitely do in order to just kind of see where you are is definitely go through, there's true and false questions at the end of each chapter, including chapter 15 so you should study those, right? And make sure that you're decently solid with all of that. Then also go back through the quizzes, right? Always go back through the quizzes. And, like I mentioned in the tips for the exam studying, if we like those problems once, it's very possible that we could like them again. Plus, they're already coded in D2L. And so, yeah, you should definitely go back and review your quizzes all the way. Why is that chair facing the door trying to kill someone's toes? I don't remember why I moved it over there. No, I think, I wanted to show my wife something over here, and she needed to, so I got the chair out. We have like storage over there. I'm in my basement right now, and then brought it over here and set it out, and then I was lazy, apparently. There's another cat in that room, by the way. My wife and I, we foster a lot of cats. My wife runs the cat cafe here in East Lansing and whatnot. And so that's just my life now. I never knew this was going to be my life, but it is my life. And I've always had cats growing up and things like this. And so I quite enjoy cats, but trying to not become the crazy cat person, but I don't know. Maybe it's just inevitable. With the current higher average being shown, what would you say would be the highest possible curve you would give us? That very preliminary. I have no idea. At this point, I might as well be just, flipping coins or rolling dice. I have no idea. Are the quizzes a good way to study? Yeah, I mentioned that already. Have a request for a particular practice exam question. That's good. Yes. Oh, yes. Someone knows my forever cat Crookshanks is, yes, that's, I now have a second actual forever cat. His name is Swashbuckler. These cats, you know, we get them as fosters. So I have two forever cats. I'm not, you know, that crazy. All these other cats will leave. We successfully have fostered a lot of cats. They will leave. But yeah, these two are the only two forever ones. So yeah. Yeah, I mentioned about the, if you have a question about your exam grade, well, I guess it depends. I mean, I'd be happy to talk to you about your exam grade, but also there's an instructor who's specifically in charge of partial credit. And so if you want to, if you have any questions about partial credit and whatnot, then you should really talk to this person. Time to add dogs to your cafe. Okay, so we're kind of teetering out on the exam administrative questions. I do appreciate these and everything, but I don't know if they'll hold up, you know, as people go and they watch this video being posted later on. I'm not sure if these would be helpful questions to them. So it's probably time to go ahead and head into the exam, some actual math here. And then we'll, so that's this, right? The second part of my agenda is doing some specific problems, just that I hope are relatively fresh for a large majority of folks. And then we'll go into an open format and I'll be taking your questions. I don't know. Yeah, this is a little bit muddled here, but there's not so many unanswered questions. So I'll try to go back through these here in just a little bit and close out any of the ones that I guess either are about cats or I feel like we've talked about. So again, this exam right here is the fall semester 2018 exam. As far as I can tell, these problems haven't been highlighted anywhere in the D2L practice exam or in the class review sessions and whatnot. And so I thought these would be a good set of problems to go over together here. So I'm starting off with problem number 2. This is the first one that would be appropriate to be on our exam. It says to express this triple integral below here in spherical coordinates. So it tells us how to transform this. And we have that the region is a hemisphere. And it looks like it's the top half of the hemisphere here. And we like to switch this into spherical coordinates. So of course, I think the easiest thing to switch into spherical coordinates, or really to switch coordinates at all, is the function that you're integrating. So in this case, we're given a specific function, and we said, well, this is one of the things that we have to switch into spherical. And so of course, E is a constant. We don't need to do anything with our constants, but the variables here, x squared, y squared, z squared, all being added together, we should have on our formula sheet, right, that x squared plus y squared plus z squared is equal to rho squared. This is the three-dimensional radius, right? That's what rho is, the three-dimensional radius from the origin. And so we can go ahead and quickly write this as e to the rho squared. And of course, if I was to just write d rho, d phi, d theta, oh, I swear I have like all my notifications turned off. I just can't figure out this one. Whatever. But if I wrote this, I would be wrong, right? And so that's kind of why we talked about these change variables and all that sort of stuff. We need to make sure that we remember whatever we change coordinate systems, that we include this integration factor, right? This absolute value of the Jacobian. And in this case, it's this rho squared sine phi. So if you want to switch into spherical coordinates, rho squared sine phi is the thing that you need to include here in order to correctly switch the dv into the d rho, d phi, d theta. Okay, now what usually takes a little bit longer here is maybe setting up the bounds. So with the bounds here, I quite often like to draw a little picture. So although this one is probably, you know, on the simple enough side that maybe you could even argue you don't need a picture. But quite often I find that the picture helps. So we're inside of this hemisphere. It looks like this hemisphere has a radius of 3, right? So I'm just looking at this equation right here. And this is way back from 12.1, right? We know what equations of spheres look like. It's supposed to be x squared plus y squared plus z squared is equal to the radius squared. And then, of course, we can offset them by, right, if we don't want the center to be 0, 0, 0, you can shift these and whatnot. So we've learned all that, spheres in standard form. And we want only the part where z is greater than or equal to 0. So here's maybe what the sphere looks like in the xy plane, and we only want the top part. And we're going to be going out to 3 here, going out to 3 here, going out to 3 here, right? That's our region. And we're integrating inside of this three-dimensional solid, that three-dimensional solid here, the top half of the sphere. And so if we were going ahead and integrating this, maybe the first thing that we need to think about is our rho, right? So rho, again, is supposed to be this three-dimensional radius, and we have to think about how do we enter into the region and how do we exit the region. And so again, kind of rhos, they start off at the origin and they emanate outwards, right? And it seems like, well, once you take the tiniest step away from the origin, you are in this region of integration. Let me go ahead and I'd like to color this. I quite often like to shade my regions. So that right there. So as soon as I take the tiniest step away from the origin, I am inside of this region. So after rho equals 0, I am inside of this region that I'm supposed to be integrating over. And then the way that I exit through is through the surface of this sphere. So the surface of the sphere is when x squared plus y squared plus z squared is equal to 9. Right? We, of course, it's solid. So you want all the way up to 9, but then, of course, less than it, right? Because it's supposed to be the solid. But the way that you actually exit is at the boundary when it's equal to 9. And so, again, this is supposed to be rho squared is equal to 9. And so, therefore, rho is equal to 3 once you take the square root on both sides, because rho is supposed to be just positives, right? In this class, r and rho are always positive numbers. And so that way you don't have to worry about the -3 at all. So there we go. That's a good setup there. It looks like there are no restrictions for theta. So I mean, at any time you could think about the thetas, and hopefully you'll get that 0 to 2 pi, right? So the only things that we really have are the sphere equation and this equation z is equal, well, z is greater than or equal to 0. So the boundary is happening when z is equal to 0. And what we'll see when we transform this into spherical, this turns out to be a restriction on our phi. So if I transform this, again, using our transformation equations, these are on the formula sheet, into spherical, we get rho cosine phi is equal to 0. So that is either rho is equal to 0, and we've already taken that into consideration, right? Certainly there are lots of places in the solid, though, that rho is not equal to 0. It goes all the way from 0 all the way up to 3, or cosine of phi is equal to 0. And of course, there's a place where cosine is equal to 0 on the unit circle. It's when phi is equal to pi over 2. So this is kind of more the algebraic viewpoint. So this is going to, our phi's are going to range from 0 to pi over 2. But let me also talk to you really quick about the graphical viewpoint. And that way, maybe you say, well, why is it 0 there, right? Why isn't it something else? And so remember phis are supposed to be this angle that are away from the positive z axis. And whenever we're thinking about our region of integration, right, our bounds, it's when do you enter into the region and when do you exit the region? So certainly when we start up here at phi equals 0, we're pointing straight up towards the positive z-axis. Do we hit the region that we're supposed to be integrating over? Well, absolutely, right? We hit it lots and lots of times. So phi equals 0 should certainly be included in this. And as you continue down, right? So again, the phi's are the angles away from the positive z-axis. And as we continue down, we continue to hit the region that we're integrating over, right? And as rho ranges from 0 to 3, we hit the region. And then all of a sudden, at pi over 2, right here, at pi over 2, the angle from the z-axis is 90 degrees, pi over 2 radians. And we just barely skim, right, the bottom of this hemisphere. And then after you continue at all more than this, right, and kind of, it's a little bit strange because, right, I can't turn my 3D picture or anything like this, but when you start aiming downwards, below the XY plane, you no longer have positive Z values. And so this ray right here never intersects the region at all. And so once you've made it past pi over 2, you would no longer want to include those values for phi because you're not hitting the region at all. So that's why this right here would be the correct setup. Notice that this just said setup, but do not evaluate. All right, so that's kind of my spiel. I have one more thing that I think I want to talk to you about for this, but I'm going to go into the Q&A for a second here and see what's going on. So some requests for some other problems. That's great. How can I prepare for this exam? Because I studied 25 hours for exam 2 and got a 22%. Yeah, so I hope things like this will help you. Oops, I lost this one. I say answer live. So I hope things like this will help you. But again, the big things, and unfortunately, you're not alone with this, is that I've heard other students, even with in-person classes, they've come to my office and things like this. And I remember I had several students in different semesters and whatnot come and say, when I went to study for the exam, I went and I redid every single WebWork homework problem, right? And so first of all, I thought, wow, that's a lot of work. That's a lot of hours and stuff like this. And for me personally, at least, if I did that, and I've had this experience going through undergrad and everything, I know that if I did that, very little of it would stick, unfortunately. I know that once I got to the exam, I'd probably be able to see something. I say, I know I've seen something just like that. But there was plenty of times where I said, I have no idea what to do. And so your game has to be not just witness a lot of math, but try to do things that help you actually be able to recall it. And so I know it's sometimes silly things. I mean, kind of very general test taking strategies actually have value when it comes to things like this. Things like making a concept map or kind of making an outline of the sections, things like that. So that way, when you see a problem, you need to know, kind of at least have an idea how to make progress with this. And especially in these sections where you just can, maybe, you're given a double or a triple integral and it says, hey, evaluate this thing. This one's nice. It says use spherical coordinates. But if you're just given a double or triple integral, how do you know if you should use Cartesian? How do you know if you should use polar? How do you know if you should use spherical, right? And so kind of doing some of those things like concept maps or making outlines of sections and things like this. And like maybe you include in your outlines like some of the most common, what you think would be the most reasonable problems from WebWork that could be asked. That would be one way that I'm thinking. Of course, right, I would need to sit down with you and talk to you about your specific study strategy, and everyone's different and it's very difficult, but that's at least my initial thoughts. Let's see, it looks like some folks got about the true false. That's good. When would there be restrictions on theta? So I guess I didn't talk about with theta, another way to see it graphically, right? So I talked about phi, right? I did the algebraic standpoint and then I did the graphical standpoint. So the algebraic was, hey, there's an equation down here that sets the limit on phi, right? And so one thing you could notice is that there's limits on phi and there's limits on rho, and that's about it. But there haven't been limits really on thetas given the equations here. And then I went over and I did stuff with a picture. We should also do stuff with a picture with theta, right? Just like how we had phi that comes off the positive z-axis and comes down, we can think about, right, theta. Theta comes off the positive x-axis, right? And then as your theta values get larger, you kind of rotate about the z-axis here, right? And again, you could ask yourself the same sort of questions. You could say, well, when do I actually hit my region of integration? And as you turn in a circle all about here, notice that there's always places where you're hitting the region that you're integrating over. And so you want to include the full circle, right? All the way around, there are points that you want to include in your integral. If you were to restrict and just do theta equals 0 to pi or something like this, you'd only get the front half of the sphere, right? The one that's with the positive y's and stuff like this. So, and then there would also be some analog that comes with the equations. You would see in the equations that there ought to be a restriction on theta. Yep, there's a free version of the textbook online. Thank you for that. So for tomorrow's recitation, we can ask any questions to our TA. Yes, so open questions for tomorrow. Which Weber quizzes? So good, someone got that one. Thank you very much. Talks to the cafe. When will the reporting be posted? Well, as soon as, right, after this, it has to process for a while, but I plan on posting it tonight. Can you zoom out a little? Okay, that's easy enough. Jacobian is the way that I say it, but I'm sure there's different pronunciations. I know that, for instance, there's, I usually say pi and phi, at least I think I do. Well, it's definitely for pi, but I know that what like British folks and whatnot say p and phi. So instead of pi, p, and instead of phi, phi. So I'm not sure if that's something like that. 15.5 and 15.6, yeah, there's no Weber hallmarks about these. So 15.5, I think, is some mass from density and stuff like that, and some other applications. 15.6 about surface area. Yeah, neither of those are on the exam. Would it be able to use a couple colored pencils for the exam? Yeah, that'd be fine. Is there a max phi for the sphere? 0 to pi. Yes, so phi always has the maximum, right? You look straight up to straight down. Any more than that, you start duplicating things. So yeah, 0 to pi is the maximum. If there are no restrictions on phi, then it'd be 0 to pi. Yes, that's true. Why wouldn't it be from negative pi over 2 to pi over 2? More specifically, the bounded comfort apart. Never mind, I got it now. Okay, cool. All right. Rho squared sine phi. Okay, I think I have that. Answer live. Oh man, when I started answering questions about this, there were 18, and now I'm up to 26. And I've gotten through a fair number of them, right? I've answered 36, but maybe this is just, I need to learn my lesson that no matter how many questions I answer, otherwise it'll be all, 90 minutes just about this one question here. Let me bring up one thing here, and then I'm sorry if I didn't get to your question. It just didn't get upvoted enough. And hopefully some other questions of yours do get upvoted enough. And if you have a question, right, make sure you upvote other folks if you also have that same question. But the one thing that I wanted to bring up is, how would you make this a D2L question? Right? How could you turn this into a D2L question? One of these where you do not evaluate. And by the way, the evaluation for this would be very difficult just because of the rho squared here, both in the base and in the exponent of E. So the evaluation, very, very difficult. That would be a lot of time to actually evaluate this one out. And that's why, of course, this exam did not ask for that, but it was more interested in the setup. And so there's a couple ways that I thought about how maybe you could turn this into a D2L problem. Of course, if you did the practice exam in D2L, you saw that there was some multiple choice that were similar to this. So they did something like, here is A, and here is like B, or something like that. And then they have multiple choice and they say, okay, what's the right value for A and for B? And they just kind of list these out. But you could also go so far as do like a C here, A, B, and C. And I was thinking about if you wanted to do a free response style question, you could ask, what is the value of A plus B plus C? Right? And that just kind of makes sure that you have all three of these relatively correct. Of course, we know that we had 2 pi for A, we had pi over 2 for B, and for C, we had 3. So you could just add all these together, and that's not unreasonable to plug into your calculator and whatnot. And whatever the decimal answer for that is, that's something that you could certainly plug into D2L. So this would be another way that you could have to know what the bounds are at very least. I don't think you could maybe capture everything, like for instance, the fact that you have to do the rho squared sine phi here, but at least that you had all of the bounds correct. Because if you have any of those incorrect, then that would be off and it would mark you wrong when you added them all together. So that was another way that I was kind of thinking that'd be kind of clever there. So, okay, let me check chat one more time, see if any of these things have come up the ranks here. I don't know. I clicked, I had answered that, but I didn't. I'm sorry. One thing that's popped up here a little bit higher on the exam, will you specify which method we should use? It's possible that for some questions, yes, but it's not guaranteed. It's very possible that they could just give you an integral and say, hey, evaluate this thing. I do see what there's at least some folks here maybe with raised hands. Do they come to the top, or maybe they went up and went down? I'm not opposed necessarily to calling on someone with a raised hand. If anyone has a question that you can't really type. Tips for solving different definite integrals quickly. So yeah, later on when we actually get into some evaluating these things, I think that I can give you some tips, but a lot of it comes down to this Fubini's theorem stuff. Foolproof method to determine whether to use cylindrical or spherical. Let's see, there's a suggestion here. I'm not sure if anything's necessarily foolproof. I mean, and that's just like a lot of things in math, right? Is that you try something, and if it works, great, and if it doesn't, just you have to know to back up. And especially with integration, like in Calc 2 and stuff like this, how do you know when to use integration by parts versus U sub versus partial fractions versus any of these other methods? It's that, well, you get good at identifying 90-95% of them. And then some of them still you'll end up scratching your head at. And so I wouldn't say necessarily it's 100% or completely foolproof. But you should be able to get to a point where you're at 90 or 95% that you can identify correctly. And then the other ones you say, I'm going to try this. If it doesn't end up working, then I'm going to back up and I'm going to try something else. Very similar to when you were integrating stuff. I know you can find a volume using both double and triple integrals. How do you know when to use which? So a double integral can find a volume between one interesting surface and the xy plane, right? And so that one interesting surface is the f of xy that you're actually integrating. Whenever you want to find the volume between two interesting surfaces, right? And so aka one is not just the xy plane or z equals 0, then you would need to use a triple integral. How can you tell which method of integration to use if you're not told? So certainly there are typically hints with these things. So like even if this one didn't say use spherical, the fact that you're over a sphere is really pushing me towards spherical. Likewise, if you're have a part of a cylinder, that's really going to be pushing me to cylindrical. Cones can do a decent job in either one. So cones, we've seen a fair amount in both the cylindrical section and the spherical section. And so those aren't usually a great identifier. However, things like paraboloids are typically in like the cylindrical camp, I suppose. All right, could you potentially have a question using change of variables for triple integrals? No, I don't think there were any, I don't remember any change of variables for triple integrals, like in the arbitrary sense, like 1510 formally goes into. I don't remember us doing anything like that in web work. And so I would be very surprised if there was anything like that. Oh, and a question about this, why use 0 to pi over 2 instead of negative pi over 2 to pi over 2. If you do that, you hit every single point twice. And so you end up getting double what you were maybe expecting. And so if you use negative pi over 2 to pi over 2, so let's say, for instance, let's just choose one particular point and I'll show that you can hit it twice, right? So let's just, for simplicity's sake, I'm going to go ahead and choose this point right here. So this point has the equation 0, 3, 0. So it's along the y-axis, and it's just on the very outskirts of this. So one way you could do this is, of course, if you're pointing in this direction here. So let's say when theta is equal to pi over 2, in order to go in that positive y-axis direction. Of course, phi is going to be equal to pi over 2. So this is kind of the standard way. And then rho is going to be equal to 3, right? So this is one way that you could get that point. However, if you also include from negative pi over 2 to pi over 2, then you could go backwards, right? So instead of just going forwards with your phi's, you could go backwards with them, and you could go down here to negative pi over 2. So here phi would be equal to negative pi over 2. That gets you into the xy plane still. And instead of going, in this direction here, you could go what in theta equals, since this would be going backwards, you would be doing 3 pi over 2. And rho is equal to 3. And that will give you that exact same point, the 0, 3, 0. So your integral will end up giving you twice as much as you were thinking, because you're just hitting every single point twice. Yeah. I was wondering if you got a 100% on the exam or the quiz, would you automatically get your, wait, it just still need to be reviewed. It would still be reviewed. Yeah, so it wouldn't happen immediately. It still gets reviewed. Okay, so I think that's probably good for the time being. Let's go ahead and continue for another problem, and then I'll go back to the question and answer here. So the next problem that I thought would be appropriate was question 4. And this one has a little bit more computation behind it, admittedly. I had someone ask about this on Piazza as well. So D is, let's see, D lies within the cylinder, x squared plus y squared is equal to 4, and bounded below by the plane z equals 0, and above by the plane z equals 6. So let's just do a quick sketch here. So we have, here's x, y, z. Within the cylinder, x squared plus y squared is equal to 4. So remember back in our 12-6 days, right, we see that this is missing a variable, and so it's going to be a cylinder. So of course, if it was just in the xy plane, this would be a circle of radius 2. So it looks something like this. So circle of radius 2, this goes out to 2 here, so on and so forth. But no matter what the z value is, whether it's z equals 0 and you're in the xy plane, or if your z equals 1 or z equals, I guess the ones that we're very interested in is that z equals 6 up here, or z equals, negative 100 or whatever, right? It's just the same copy of the circle over and over and over again at every different z value, because again, this circle here doesn't depend on z. This equation here doesn't have any z's in it. So this would technically go on forever. It's an infinite cylinder. And they say, well, wait, we're not going to do some infinite solid here. We're just going to do the piece that's bounded below by this plane z equals 0. So this is going to be our starting height, and above by the plane z equals 6. So let's say that this is where z is equal to 6. And the rest of it, is perfectly fine and whatnot. We're just not interested in it in this case. And so we're asked to find, the average temperature. So the average temperature, well, we have a temperature function here, and we'd like the average of that function. And so we need to remember, right, we have some questions in web work and whatnot about average values of a function. Back in our math 132 days, or calculus 1, we also had an average value of a function. In that case, it was 1 divided by b minus a, the integral from a to b of f of x dx. And so basically you were on a piece of the x-axis from a to b, and this right here is just the length of that piece that you're considering. So in this case, it's from a to b. So if you think about like 1 to 5 or something like that, the length from 1 to 5 is 4. The formal math way that you find 4 is that you do the subtraction, 5 minus 1, 4. If you want to upgrade that to double integrals, it's 1 divided by, and the two-dimensional equivalent of length has got to be area. So it's 1 divided by the area of whatever region you're on. So in this case, the region, I'm going to just say D, and we're allowed to have 2 variable functions now with our double integrals. And so again, this is area of whatever region that we're on. And if you wanted to do this with 3 variables in a 3-dimensional case, right? So with a solid rather than just some 2-dimensional region, well, then you would do a triple integral over your region. And the 3-dimensional equivalent of length or area has got to be volume. So it's going to be 1 divided by the volume of your solid. And then again, your function can have, well, with the triple integral, it can have 3 variables, x, y, z. So this is the average value of a 1-dimensional thing, 2-dimensional thing, 3-dimensional thing, right? In this case, we have a 3-dimensional solid, right? And our function here has 3 variables. So this is kind of just, some preamble to all this. But what I would like to be using here is this third case, right? And luckily, right, with this solid, the cylinder right here, we know a volume equation for this cylinder, right? There's only a handful of things that we do know a volume equation for. And by the way, this is on your formula sheet. And it says that the volume of a cylinder / prism is equal to the height times the area of the base. So in this case, the height here is 6, and the area of the base, well, it's a circle, right? So the circle has the area equation of pi r squared. So in this case, it's a circle of radius 2. Again, we're looking from the algebraic standpoint, this equation x squared plus y squared equals 4. We know that the radius of this circle is 2. And so we can get that the volume of this is going to be 6 times pi times 4. So that's going to be 24 pi. So if I want to set up a good equation for this, it's going to be 1 divided by the volume, 24 pi, and then the triple integral here. And then notice that this one did not say use Cartesian or use cylindrical or use spherical, right? But I hope that when you look at this right here, that everyone has a strong push to go towards cylindrical, because after all, you're over a cylinder. And so even though it does not say use cylindrical, I would personally use cylindrical. And so I'm going to go ahead and write down here r dz dr d theta. And again, this will probably work out, but if it doesn't, then we'll just back up and we can try something else. Okay, so at this point, right, we need to convert our equation, right, the thing that we're actually supposed to be integrating, right? We want to find the average value of a function, and the function's giving the temperature. So we want the average value of the temperature, and we need to switch this into cylindrical. So I'm going to do r cosine theta for x. I'm going to do r sine theta for y. Z is, of course, just z in cylindrical, and 1 is just 1 in cylindrical. When we go ahead and we integrate this, from my picture here, we can see that we're going to go from z equals 0 to z equals 6. When we go for our radius, this is going to go from 0 to 2, and our thetas are going to go from 0 to 2 pi. So again, you can see the only 3 equations that we have that are determining our region that we're integrating about are these 3 right here. Of course, we have another function that we're actually integrating, right? Because we want the average temperature. But the 3 things that actually specify the region that we're integrating over are these 3 right here. And so you can see where the z equals 0 and z equals 6 comes from. From this one right here, you can see that we get r squared is equal to 4, or r equals 2. So that gives you that one right there. And then kind of from the picture, that helps you see that, well, r equals 0 and 0 to 2 pi should be what we're integrating over. But those are kind of the standard ones as well. So if you don't have the picture, you can probably guess this as well. And notice this thing never said draw the solid that you're integrating over. And so if you're have done enough of these and you're happy with guessing with this, then go for it, I suppose. All right, so let's go ahead and think about these things for a little bit. I don't know, I'm kind of, I'm torn here. So this is the average temperature function here. I mean, it speeds things up considerably. Just thinking about, I mean, we should be at least mildly interested in speed. Whatnot, is if you kind of think about this as there's going to be really 4 different pieces, right? So once you distribute this r to all of these things, there's really 4 different pieces. And I would like to claim that these 2 right here are going to completely disappear. So let me see if I can convince you of this. If you are unconvinced by the end of my explanation, that means you probably shouldn't use this trick and you should probably just do it out, and it'll take you an extra step or two. You'll be a little bit sadder, right? But overall, it's better to be safe rather than trying something new, I suppose, especially when it comes to the exam. So if I was to just look at this piece right here, thinking about the triple integral of, again, r squared cosine theta once we have this distributed. First, I'm going to integrate with respect to z, then with respect to r, then with respect to theta, but these are all nice constants right here. And so I'd like to use Fubini's theorem. So Fubini's theorem says that, or one of the versions, like when you have all these separate pieces, a function of r, a function of theta, a function of z, all being multiplied together, right, that you can go ahead and rewrite this. So I'd like to do a quick rewrite here and write this as the integral from 0 to 2 pi of cosine, the integral from 0 to 2 of r dr, and the integral from 0 to 6 of 1 dz. Notice there are no z's in the thing that I'm integrating here, and so you can always just do a 1 here. And so now this is easy to integrate, this is easy to integrate, but what I'm most interested in is when you integrate cosine. When you integrate cosine, you get sine, and when you plug in 2 pi or when you plug in 0, both of these cases give you 0. So you're going to get 0 times who cares, right? And so that's why this is all going to be equal to 0 here. I'll save this, but I'm going to move it down here. Oops. And of course, you can do the same sort of thing with sine. With the sine case, when you integrate sine, you're going to get cosine, though. And what you're going to end up with is 1 minus 1, right? Because you're plugging in 2 pi and you're plugging in 0. Both of those are going to give you 1 out for cosine. And so the 1 minus 1 is going to end up giving you the 0 here. So I would be very tempted, right, to rewrite this rather quickly here as the triple integral from 0 to 2 pi, 0 to 2, 0 to 6. And this is going to be zr plus, well, actually, I'll do z plus 1 times r, dz, dr, d theta. And really, you can do the same trick here, right, where you kind of break this all up. Because we have a product of just z's, a product of just r's, and a product of just thetas. In this case, there are no thetas, so you could use 1. And so I'm going to go ahead and write 1 over 24 pi here. That needs to be carried along all throughout here. The integral from 0 to 2 pi of 1 d theta. The integral from 0 to 2, let's see, that's my r's, so r dr. And the integral from 0 to 6 of z plus 1 dz. And so let's see, I'm going to have 1 over 24 pi. The integral of 1 d theta from 0 to 2 pi is, of course, just 2 pi. The integral of r is going to be r squared over 2. Of course, if I plug in 0 to this, nothing exciting happens. If you plug in 2, then you get 2 squared, which is 4 here. And when I integrate z, I get z squared over 2. And when I integrate 1, I get z. When I plug in 0, of course, nothing interesting is happening here. When I plug in 6, we're going to get 36 and 6. So this is how you can evaluate these rather quickly. Notice that we have the pi here's are going to cancel. We have the 2 and the 24 is going to cancel a little bit. This is another 2 will cancel down here. So you're going to get 6. And let me go ahead and evaluate this out. Oops, and I forgot to get rid of my squared. I already squared my 6. So let's see, this is going to be 1/6, and then we're going to have 18 plus 6. So that's going to be 24. So 24/6, or that's going to be, what? Oh, that just goes in evenly, 3. So the average temperature on this region is a nice, easy 3. Certainly something that you could plug into D2L. All right, so that's one where you have to kind of be a bit careful, do the evaluation. Again, it didn't specify what method to use. We had to decide to use cylindrical coordinates. And to get all this, and yeah, so I'm going to go into the question and answer here and see what I need to reiterate or that I missed. Where's the question to look out for the exam, like something to work through? So, okay, yeah, one of the highest ones here. What are some questions to look out for the exam, like something to work through? I'm not exactly sure what this means. I mean, so I would reiterate kind of the most important things that I would do is probably go back through the quiz questions, go through the D2L practice exam, stuff like this, things that have shown up on previous exams. I think that those, because you kind of want to get into that Goldilocks zone of like, right, some questions in web work may be a little bit on the easier side. Some questions are certainly on the more difficult side where it's kind of time consuming. And so you kind of want to make sure that you get some of these good length questions. 24/8. Oh yes, 24/6. Thank you for pointing that out. You've saved me a lot of emails for sure. So yeah, 24/6. Hopefully we all agree 4. So yeah, sorry about that. Excellent. So theta depends on the x-axis, phi depends on z. What does rho depend? Wait, does that mean rho depends on y? Rho is the 3-dimensional radius from the origin. So it's how many steps that you take away from the origin. This is one thing. So you may want to go back, right? We brought up 15.9 now twice. Once we introduced all of these variables, what rho is, what phi is, what theta is. And I did a video about that, my kind of pre-class video to 15.9, where I kind of specify all this and go into, it's kind of like if you're programming a turret or something like this, or a medieval cannon, right? You would have to say, how far do you want to look left and right? How far should you aim up and down? And then how much, I don't know, gunpowder or something you want to fill the cannon with. So that way it shoots the projectile as far as you want it to. Would we be asked to integrate sine to the 4th of phi on the exam? It seems unlikely unless if they were to give you like a hint for that. So I suspect one question that will be asked, I'm not sure though, but I had kind of prepared, there's been a lot of folks on Piazza asking about what homework 27, problem number 1. And I had some comments prepared for that if anyone was interested of how to turn that into an exam, a reasonable exam question. And so kind of with an appropriate hint or whatnot, you could turn this into sine to the 4th of phi would be a fine exam question. Where can we find this document to study? So I posted it on the link on Piazza and on D2L under the announcement. So just click on that link and that will get you there. Spherical will be on the exam. Yes, it will. Who writes the exam? So it's all of the instructors have hands in writing the exam. I probably, so yeah, since I'm kind of in charge of the assessment stuff with D2L and whatnot, I take the first draft. And so I write the largest portion of it, and then kind of we all look at it and there's comments and it gets kicked around a lot. And yeah, so sometimes it changes quite significantly. Sometimes it stays relatively close to what my first version was, but yeah, I usually take the first crack at it. Good. Do we get a formula sheet for the final exam? Yes, you will get a formula sheet. It hasn't been updated yet, but after exam 3, that's going to be one of the first things that happens. Why is theta from 0 to 2 pi if it is only a half sphere? I hope that, yeah, okay, good. This has been answered a fair amount, and it's about the previous question. All right, we're kind of down to some questions that don't have that many, I guess, upvotes or whatnot. And so this would probably be a good spot to go ahead and continue on to the next bit. I wanted to do what problem number 5 would not be so appropriate. This would be something that would be fair game for the final exam, but we haven't gone over Green's theorem yet. But something like this. Number 6 here, consider this integral. This would be a fine question that could show up for our exam. Here we've done lots with double integrals. And so we're going to sketch the region of integration. then we're going to evaluate the integral here by reversing the order of integration. And so, okay, so this one's nice. It tells us to go ahead and sketch. Of course, we've had plenty of web work problems, right, where it just says evaluate the integral by reversing the order of integration, but it doesn't necessarily say to sketch. So this is nice. It's awarding some points for getting the good sketch here. So for the region of integration, remember, you're always looking at the bounds. You're not really caring so much about what function you're going to be integrating at this time. You're just looking at what are the bounds. Those always tell you about the region. And so notice that we're integrating with respect to y first, and then with respect to x. So those will tell you what kind of values these are. Oops, I don't know why it's not. There we go. Now I'm zooming in. So the inner ones here are y's. So this is y equals root x and y equals 2. And then the outer ones are going to be the x's. So this is x equals 0 and x equals 4. And so sometimes, especially when I'm doing a triple integral or whatnot, sometimes I like to start on the outside and work my way in, just because it kind of tells me where I'm supposed to be drawing the picture. So when you start on the outside, you see that you need to somehow pay close attention to what's happening between 0 and 4. So 0 and 4, and these just usually give me my tick marks here. So x equals 0 is, of course, right here, and then 1, 2, 3, 4. So x equals 4, that's where our picture is going to stop. Because many of these curves continue on forever. And especially with triple integrals, when you're doing a three-dimensional structure, right, you really don't want to draw more than what you absolutely have to. And so this just kind of gives you a window for where your picture is going to be. So let's actually get into what we're drawing here. We're supposed to be entering into our region, right, through y equals root x. So, right, the lower limit of integration is always how you enter into your region. So root x, I know that this looks like something like this. And again, it continues on forever, but I really only care about it between x equals 0 and x equals 4. So that's where my picture is going to stop. And I don't really, right, I don't draw this stuff out here. Of course, right, we know that the square root of 0 is going to be 0 and the square root of 4 is going to be 2, just so if I want to kind of have a frame of reference. And then my upper limit of integration, how I'm supposed to be leaving my region, is through y equals 2. So y equals 2 is the nice, boring, straight horizontal line at height 2, y equals 2. So, and again, y equals 2, this line would continue on forever, right? It would keep on going over this way, it would keep on going over this way, but I'm only drawing it in that window from x equals 0 to x equals 4. And again, this is a relatively small thing here for double integrals, but it ends up being fairly significant for when you do triple integrals. And so imagine if we're traveling in this y direction, we need to, again, enter in through the y equals root x, and we need to leave through y equals 2, right? So this is the region that we're going to be integrating over here. So, okay, we have the sketch. I guess, I think I have it decently labeled, but if I was taking the exam, I'd still be a little bit paranoid, and I'd probably put 4.2 right next to that point there. Okay, so part A complete. Part B, evaluate the integral above by reversing the order of integration. And so, by the way, if you didn't reverse the order of integration here and you just were to try to find the antiderivative of this, this is extremely difficult. In fact, I'm 99% sure that there is no elementary antiderivative for this. None of the techniques in Calculus 2 would be used in order to solve this thing here. And so I'd have to verify, but many of these, there's no elementary antiderivative. There's no functions that we know that if you take the derivative of them, they would give out this thing here. I have another example later on that I'll show you kind of what some of these non-elementary antiderivatives actually appear as. But yeah, maybe just take my word, this is very difficult to integrate. And so in fact, even if it didn't say reverse the order of integration, we are stuck here, right? And so we have to know, right, one of the things that we have, in our tool belt for solving double integrals is that sometimes reversing the order of integration helps. And so even if it didn't say reverse the order of integration, we could try to integrate this for a little bit and say, man, I don't know what the antiderivative of this thing is. No idea, and nothing's working. And so maybe we need to reverse the order of integration. And so, okay, if I want to reverse the order of integration, remember, reversing the order of integration does not alter the function at all. So again, the function here is staying the same, but we're going to be reversing, instead of dy dx, we're going to do dx dy. So in this case, we have to think about if we're traveling instead in the x direction, right? So that's the one that we're integrating first. Of course, in the x direction, that goes left to right. Small x values are off to the left, big X values are off to the right. And the way that we enter into the region of integration is through this straight line right here. This straight line would have the equation x is equal to 0. So x is equal to 0 is how we would enter in through this. Remember, these have to be x values, right? So this would be x is equal to 0. There's even some textbooks out there, or maybe if you do enough Google searches or whatnot, that you'll find that they include like the x equals here in some textbooks. Ours textbook doesn't. It just kind of cleans it up. It makes things look a little bit nicer, but these need to be x values because we have the dx here. Okay, so the way that we exit, the reason why I emphasize that so much, the way that we exit is through this curve right here. Remember, this curve came from y is equal to the square root of x. But again, we need an x value. We need x equals something. And so in that case, we need to square both sides. And we get x is equal to y squared. And so we would write y squared, right? Because that's my x equals right here. And remember, for your inner bound of integration here, you're allowed to have things in the bounds that haven't been integrated yet. So the fact that we haven't integrated y yet is another kind of reconfirming that we're doing well, that we're setting this up correctly. Okay, and then for the final bounds of integration, right, we need to capture this in just numbers now. What's the smallest y value and what's the largest y value that is included in our region of integration? When do we start and when do we stop? Well, the smallest y value that we have here that's included in this region is y equals 0. And the largest y value is given by y equals 2. So this is going to be from 0 to 2. Okay, so now we can actually do the integration. So we're going to do, of course, inside out here. We start evaluating our x integral. We'll notice that this doesn't have any x's. This is constant with respect to x. And so I'm going to have this constant here with respect to x times x if I integrate with respect to x. And then I need to plug in 0 and y squared everywhere I see an x. And then, of course, I need to do my y integral. And so if I plug in y squared and I plug in 0, of course, let me skip one step here and just kind of clean things up. I'm going to have y squared minus 0, which is just y squared here. And with that extra y squared, now that we have this, because we've switched the order of integration, this becomes far more manageable to integrate with respect to y. Now this just becomes a relatively simple u substitution, where u is equal to our inside function, 1 plus y cubed. Du is going to be equal to 3y squared dy. And so notice that we're going to be trading in this y squared dy here, and we can do it for what? Du divided by 3, or 1/3 of du. Let's go ahead and find the antiderivative of this. Again, the 1/3 is just kind of along for the ride. It's some constant. When I integrate this 1 divided by square root of u, I'm going to get square root of u on top, like this. And then, of course, if I was just to leave it as is, I'm missing something, right? If I was to take the derivative of this, I would not get quite back to where I started. Because remember, the square root is the same thing as the 1/2 power. So, but notice if I take the derivative of this, right, a 1/2 would come down, right? And there's not a 1/2 back up here, right? And so I need something to cancel out with a 1/2. And so according to the power rule, right, it needs to be the reciprocal of whatever that new exponent is. The new exponent here is 1/2. And so the reciprocal of 1/2 is 2, right? And so we need this 2 square root of u. And now if you take the derivative of this, you get exactly back to where you started. Of course, u in our case is this 1 plus y cubed. And we need to evaluate this from 0 to 2. And so let's see, I'm going to get 2/3. And let's see, when I plug in 2, I get 1 plus 2 times 2 times 2, 1 plus 8 is going to be 9. And when I plug in 0 here, I'm going to get the square root of 1, which is 1. And don't forget this 2/3 needs to be applied to everything. And so let's see, this is going to be 3 minus 1 is 2. So my final answer is 4/3. 4/3 is my final answer here. All right, so that's how we would solve this one here. I'll go ahead and pause and see if there are any questions about this. Again, make sure if your question aligns with someone else's, please upvote it so it comes to the top here. Right now, the top ones I see here would changing the bounds on phi from 0 to 2 pi, taking the volume of the whole sphere and then taking the half integral be correct too. 654. I don't know. Assuming that that would have been back in our only spherical one. But let's see. You have to deal a lot with the symmetry. If you're going to do tricks like that, you have to be awfully sure that the function is symmetric. And so I'd be a little bit worried about doing tricks, especially if they're not gaining you much. Six to an 8. All right. I don't see. I'm getting now a lot of these questions about my mistake for the previous one, but not so much about anything this. Okay. Oh, it looks like we have one person who has a raised hand. We'll go ahead and try this out. Allow you to talk. What's up?
Hi. I was just wondering if this would if we would have to define this question as type 1 or type 2, or on any question define it, like if you'd say do this as type 1 or something like that. Like, do we have to know the difference between type 1 and 2 for tomorrow?
I haven't seen a question on any exam in the past, I don't know. How long have I been here? 8 years or something like that. I haven't seen anything that asked about type 1 or type 2. This
Amazing.
is pretty arbitrary based on the author. And so,
awesome. Thank you.
Yep, no problem. Allowed to talk.
So I'm pretty sure I have a vague understanding of it. I know that phi usually goes from 0 to pi.
Yep.
In the case that phi is not from 0 to pi, is it because you're taking the z values and putting them equal to each other, and then finding what value for phi it must be for them to be equal? Or how are you finding the phi values if it's not the standard value? Is that how I should say?
Yeah, so typically there would be, so you could view it either from the viewpoint of graphically, in which case, so you could go to, I guess our one spherical so far has been this one. And so when you look at the graph, you could say, I am hitting the region as phi, right? Remember, phi comes from the positive z-axis. So if I'm pointing straight up, I hit the region of integration. And as I go down all the way to 90 degrees, or pi over 2, and then after that, I start pointing down, right? And when I'm pointing down, of course, I'm not going to hit anything where z is supposed to be greater than or equal to 0. Here, I'm not going to hit 0 or above. And so that's where you should stop. So that's the graphical viewpoint. From the algebraic viewpoint, usually it comes down to one equation, not necessarily setting multiple equations equal to each other. But in this case, we did a little bit how this one equation, when z is equal to 0, that specified the bounds of this region. If you go ahead and you take this and you solve when does this occur, and you transform it into spherical and you solve that, out pops phi equals pi over 2. So quite often this is more typical.
Okay.
Awesome. Okay, let's go back, and I just want to make sure that there no other questions in chat have popped up. Will you ever ask to go from cylindrical or spherical to Cartesian? Not that I can recall. Can't recall any time that we've done that. I guess it would have to be set up very nicely, I would say, if you were to ask to go from cylindrical or spherical into Cartesian. Everything would have to be very obvious, I suppose. So it wouldn't be a very difficult question, I would say. I have a request to go over a question again. Sorry, I'm not sure which one it was, but remember I'm recording here and I will be posting this. And so certainly you can rewatch this and you can, change the speed and all that sort of stuff and go over parts again. And then if you still have questions about that, please post them on Piazza and I'd be happy to talk, reiterate things or kind of explain a little bit farther there. But I probably will not be going over the same question again. Let's see. Okay, so let's go ahead. Moving on, this question right here, I think got asked in the first time we were doing 15.9, where we were just introducing the coordinates and all that sort of stuff. These right here, absolute maximums, that was on exam 2. This was on exam 2. This was on exam 2, exam 2. Exam 2, all of these. I think the next one is 16. So 16 here is one that a triple integral, and it just says evaluate this thing. And this right here, I think even though it's a multiple choice question, it ends up being a rather difficult question here, because if you were to just leave this as is and you were trying to integrate with respect to x first, notice the only x's here are cosine of x squared. Trying to integrate cosine of x squared. And again, if you were to, spend an hour or two trying to evaluate cosine of x squared, that integral, you'll end up spinning your wheels for that entire time. You can spend maybe a year or so trying to evaluate this thing. And again, this is a very difficult, in fact, impossible integral to do. In fact, I'll show you really quick. I'm going to switch over to my desktop quickly for this, but imagine like the first time when you were integrating 1 over x dx, it's kind of, similar to this. And that the first time anyone integrated this thing, there was no way to explain what this was in terms of any other functions, no matter how many square roots, cube roots, squares, sines, cosines, anything like that. And so what you do is that you define a new function. And the earliest definition for the natural log is just the antiderivative of this thing. And so they made up a function to answer the question that they wanted an answer to. They just said, what is the integral of 1 over x? I don't know. We're going to call it the natural log, right? Because we couldn't create it from any of the previously known functions. And so if you try to integrate cosine, and let me take over really quick with cosine of x squared. I have it here. Before class, I typed this. Oops, no, that was a different one. That's kind of related to this homework 27 problem number 1. But if you type this into Wolfram, you get here, this is the answer. You get C of, right? They just have the square root of pi over 2 and then C of, and you say, what is C? I've never heard of this thing before, right? And so you have to do a little bit of digging, but this is called the Fresnel Integral. And it is the answer to that you want an answer to, right? It's just defined as the integral of cosine of some variable squared, in this case, t squared. And you can do a whole lot of fun things with those. And it turns out they're pretty interesting and all that sort of stuff. They have to do with Euler spirals. And there are some real world uses for this thing. But again, this is just something that it's an answer that we needed an answer to. And we didn't have any way to build this from any of the previous things that we've made. And so you have to define it as something new. And so I understand that maybe that's not super, I don't know, compelling or super, it's not a happy end to the story. But hopefully you see that yes, we've done this before with the natural log as well. So this is not like an unheard of thing that you just kind of, you define a function to be the answer that you're asking a question for. And so yeah, this happens periodically anytime you need a new function. And so, okay, hopefully I've convinced you, right? Because again, I said, if you tried to integrate this thing, oh no, screen sharing ended unexpectedly, it says. If you tried to integrate this thing, you could spend an hour, you could spend a year if you wanted to, you could spend a very long time trying to integrate this thing. and you would just spin your wheels because there's no way to do it with any of the things that we've built before. Let's see if this is going to freeze again. No, it looks like it's better now. My best guess is that it's like somehow has to do with like processing speed or whatnot, but every once in a while, if I switch too fast, it seems to freeze out on me. So if we cannot integrate with respect to x first, what must we do then? How can we make any progress on this question if we cannot integrate with respect to x first? Well, we have to change the bounds of integration, right? That's one of the things that we have in our tool belt, is that if you can't make any progress with this, maybe changing the bounds of integration would be useful. So we're going to try to change the bounds of integration on this, which means that, well, we need to look at this here, and we need to see what it looks like, right? Draw some pictures and whatnot, and then we're going to change the bounds of integration. So, okay, we're going to draw x, y, z. Here, space. And again, when I typically do this, I usually work outside in, just so I know where I'm drawing things. So first of all, looking at my outer bounds, I see z is ranging from 0 to 4. Remember, by the time I get here, this is just kind of specifying my window, my little tick marks. There'll be no more x's, there'll be no more y's, there'll just be z's left, right? And so z is just these numbers from 0 to 4. So I know that's kind of, it's got to be somewhere in here. This is going to be my window from z equals 0 to z equals 4. So I know I don't really care about anything with negative z's. I don't care about z's that are greater, 5, 6, 100, stuff like that. But 0 to 4 is where my picture is. Now, if we kind of move inwards a little bit, we see our y values go from y equals 0 to y equals 1. So thinking about if I was in, right now we have y's and z's to play with. So if you were to do y equals 0 in the yz plane, y equals 0 is going to look like this. And again, kind of we're framing our window here right now. So 0 to 1, that's probably too far. Let's just do like this, 0 to 1. So y equals 0 is pushed up all the way, in the xz plane. So y equals 0 would look something like this. And then y equals 1 would be the straight line here. So this is kind of the window where my picture is going to be. And then finally, we need to look at our z values. And these are, of course, always the most complicated to draw. I'm going to do, I don't know, black, I suppose. So x values. So we have x equals 2y is how we're supposed to be entering into this. And x equals 2 is when we're done, when we exit our region of integration. So x equals 2 is probably the nicest thing to draw. X equals 2 is just a nice flat plane. So something like this. So here's maybe 1, 2, and x equals 2, again, kind of this plane, it goes on forever, and it's this very big thing. But again, we only really care about it in this particular window. So I'm going to go ahead and just kind of frame it in this particular window here with all of my bounds, right? Y is supposed to be from 0 to 1. Z is supposed to be from 0 to 4. So even though this plane goes on forever, we only want the piece that's in this window here. And then the last bit here is supposed to be, and the most complicated, and that's why I saved it for the last, is this x is equal to 2y sort of deal. And again, this is going to be a plane. It's a plane, it's missing its z variable. So technically, right, you can go up and down as much as you want here. And as you could probably guess, it's going to kind of connect these here, right? So 0, 0 is a point on this. And then also if y is equal to 1, x is equal to 2. So again, y equals 1, x equals 2, right? So these kind of connect very nicely. So what you end up making is this wedge sort of deal. So again, if we were traveling in this x direction first, we would first go into this flat surface right here, this x equals 2y, and then we would leave through x is equal to 2. So this bit right here. And that green box right now is just a shadow, right? Again, this just was telling me where my pictures are going to lie. So that way I don't have to continue drawing this thing forever. I can only draw the pieces of it that I absolutely need. So that green box is really to just kind of frame everything. Quite often though, 0 does end up being one of these pieces. So I mean, if x equals 0 was a piece, then you would actually end up using this exactly. So, okay, now I have what the structure actually looks like. When I'm looking at this thing and trying to decide how should I integrate, well, I know I definitely don't want to integrate with respect to x first. We tried that, it didn't work so well. But looking at the function again, I guess, certainly not x's. Z's would be okay, I guess. But if I'm just looking at the function, I see that there's no y's. So maybe y would actually be the easiest thing to integrate, just because there are none of them in this function itself. And so, okay, let's try to integrate with respect to y first. So I'm going to go ahead and set up my integral, and I'm going to be integrating with respect to y first. So yeah, you can end up seeing why they left the 4 and the 2 here, but I'm not sure if it's obvious at this point. I would probably just simplify it here. 2 cosine of x squared and then divided by root z. It doesn't really make it any more complicated if you do that simplification. So if I'm integrating with respect to y first, well, then again, I have to think about I'm traveling in this y direction. So here's the y direction. The large y values here are along the positive y-axis, and the smaller y values are back here, right, along the negative y-axis. And so if you imagine, right, I'm traveling in the y direction, how do I enter and how do I exit this region that I'm supposed to be integrating over, this wedge? And so it looks like I end up entering, and I'm going to do red here. I end up entering in through this back panel right here. This back panel, this is seemingly, if I'm traveling in the y direction, I enter in through this. And it's maybe not surprising here that this is given by y is equal to 0. Y is equal to 0. And of course, you even see when you were doing your y bounds of integration, you see a y equals 0. So maybe that's not super surprising here. And even though that the largest y value is 1, right, the way that you end up exiting this region of integration is now through this slanted piece, right? Because you're doing this y integral earlier on, kind of you get a more interesting surface. It's this black surface right here, which of course came from x equals 2y. And so if I want to do a y bound of integration, I need to solve this for y. So this is going to be y is equal to x divided by 2. And this is kind of very similar to what we did before with the whole y equals square root of x. We squared both sides to solve it for x. So here we're solving it for y, and we get y is equal to x over 2. Now, if you were kind of done integrating with respect to y, right, again, you have to imagine once you've done that, there are no more y's. There's just x's and z's left. And so what I usually imagine is that I take this structure here and I smush it, right, into the xz plane. So when you smush it into the xz plane, it just becomes this kind of this red piece that I had done as kind of like a shadow here, this back panel, right? And so it's going to look like this. Maybe I'll draw a quick 2D picture here and just kind of reorient things well. So again, the largest x value ends up being x equals 2, and the largest z value ends up being z equals 4. And again, I've taken this and I've taken away all the y's. I've just taken this and I've smushed it into the xz plane. And so now this is what it looks like, a nice, beautiful rectangle. And so, well, I don't really know. Again, maybe I'm most afraid of x. I don't want to integrate x. I'm not looking forward to it. And so maybe I'll integrate with respect to z next. And so if you were integrating with respect to z next, you're traveling in the z direction. We need to think about how do we enter and exit this? Well, you enter in through this straight line right here and you exit through the straight line. Those have the equations z equals 0 and z equals 4. And then finally, for our final bounds, what's the smallest and largest x value in our region? It's going to be from 0 to 2. All right, this is by and large the hardest part, is setting this thing up. Now the evaluation goes rather smoothly, actually. So let's just do the inner one here, and then it gets even nicer. Oops, and I forgot to include my dx here. First, we're integrating with respect to y, and there are no y's. So we're going to have, this is all nice and constant. So 2 cosine of x squared divided by root z. and we're going to have a y, and we need to evaluate that y from 0 to x over 2. And so when you plug in x over 2 and you plug in 0, let me just skip one step and put it all right here. We get x over 2. That extra x right there will end up saving us completely. That extra x right here is the thing that turns this from a completely unreasonable, horrible function, right, where the integral is this weird Fresnel integral, right, and it instead turns it into just a u sub, and it's very nice. So we can go ahead and cancel the 2 here on top and on bottom. We still have a z integral and an x integral to go. And so now we see that we have nice constants here. We're over a rectangle, and we have a product of a function with just x's and a function with just z's. And so, well, according to an extension of Fubini's theorem, you're allowed to do this. You're allowed to put all of your x's together in one integral here. So x cosine of x squared dx. Put all of your z's together in one integral. So the z's would be from 0 to 4 of 1 over z squared, square root of z dz. Evaluate both of those on their own and then multiply the results together. So again, this one right here ends up being 2 root z evaluated from 0 to 4. Double check, take the derivative, you'll get back to where you started. And then this one right here ends up being something pretty close to sine of x squared. But of course, if you take the derivative to try to get back to where you started, notice that when you do the chain rule, you would get 2x, but we only have an x here. So you need something to cancel out with that 2. It's got to be a 1/2. Now double check, if you take the derivative, you'll get back to where you started, 0 to 2. So let's go ahead. If you wanted to, you can see the half and the 2 here will cancel out just fine. We're going to have sine of 4 minus sine of 0. Sine of 0 is just 0. And then times square root of 4 is going to be 2, and square root of 0 is going to be 0. So it's going to be 2 sine 4. And here, this happened to be a multiple choice question. The answer is 2 sine 4. So we would select that and be done with it. A long multiple choice question, right? This is definitely one that, you know, if I came across this on our exam, right, a triple integral and one that I couldn't integrate quickly, I would save it for last, right? I'd say, oh, that's a tough one, right? And for 4 points, you know, I mean, I don't want to give away those 4 points by any means, but it's one that I would certainly do last, just because it's going to take some time, right? And of course, if this was something where you had to enter it into D2L, always, always, always radians, right? So double check, be paranoid. Sines and cosines, right? These are always radians. And that's just because as soon as you say that you want to integrate sine or cosine, in this case, you were integrating cosine, this only works, right? The derivative of sine being cosine, for instance, only works if you're in radians. If you're in any other units, degrees are, of course, the most common ones, this is not true. And so anytime that you're doing calculus, you are always in radians, just because otherwise some of these very extremely basic things that we really want to be true are not true. And so that's why you have to be in radians. All right, so let's go ahead and, wow, it's 8 o'clock. I did not act as fast as I was hoping. Let me go over maybe some quick things here in chat and make sure that at least those are answered. And I hope that this has been useful for you. You will have some time in recitation, of course, and I have office hours tomorrow where you can come and ask more questions. So I'm sorry, I had dreams of being able to take more student questions as far as, you know, what some math to do together, but I did not get there. But that's going to be my entire time in my office hours tomorrow from 2 to 3:30 p.m. The links on the syllabus, it's kind of my normal Zoom link and whatnot. And then, of course, the recitations. The recitations are a time to come ask questions as well. I feel like I'm losing my voice. Anyway, So where can you find this video? Yes, I'm going to post it on at least Piazza along with my other office hour video and whatnot. So yeah, this will be posted at least on Piazza. I'll maybe try to find a spot for it in D2L as well. So, all right, guys, I hope that this has been useful. If you have any questions, again, I'll post this. If you missed anything, please go back and watch the video, and I'd be happy to take at least some questions on Piazza as well. But especially if we need a little bit of a back and forth, come to my office hours, because right there it's just like a Zoom meeting where you can show your video if you want. You can ask questions. Anyone can unmute themselves and whatnot. And so yeah. All right. Thanks, guys. I'll try to answer a few of these questions coming in, but then yeah, I'm gonna get going. Post it in your pre-class video. Okay, so like on D2L. So yeah, maybe down below there I could post it on that D2L page. Yeah, that seems reasonable. Q&A, there's still 57 open questions. There's no way I'm gonna be able to get through all of these. Seeing if there's any ones that are fast. So someone asked about the type 1, type 2. Is there any integrals where you would not be able to split this up? Yeah, so unless if you have a product of things, then that's the only time where it works. So yes, or if you had, I like this example where you have cosine of x times z, then there's no way to split that up. So, but the simplest is if you just had something like x plus z. There's no way to split that up with multiplication. So the multiplication is also very important there. All right, lots of thanks, excellent. Where is this practice exam? Okay, everyone got that, good. All right, I think we got at least all the ones. Let me make sure. I don't know what the new method is. I'm sorry, I'm going to clear that one. Can you do a triple integral the traditional way? In office hours I can, but not here today. I'm sorry. I agree. Homework 27, number 1 would have been useful to go over. I'm sorry that we didn't have time for it. Can you do one of the practice exams similar to something like that? Actually, so this changing the order of integration here was very similar to that one on the practice exam, I believe. And so we did indeed something like that. Can you do practice exam 3, question 2? We did that in my office hours on Tuesday. Go and watch that video. We did that one. So yes, we in fact have done that. And then I have one hand raised, and then this will be the last thing. And then I'm gonna go do something else. I don't know. What's up?
Hi. I just had a quick question about how to use the browser calculator with e to the x, because during my last exam, I couldn't get it to work.
Yeah, and it's very similar to when you in like the first quiz or so, when you wanted to do cosine inverse, right? So you see a cosine button and you want the inverse of that. And so there's an inverse button. It's just INV. And you hit that inverse button and then it pops up cosine inverse. And likewise, there's a natural log button on the main screen. And if you hit the inverse, of course, we know the inverse of the natural log is E. So you hit that INV button and then you can get that. And I know it's maybe arguably late or whatnot, but in the semester, but I was trying to emphasize to everyone that if you have the $10 or whatever, the TI-30, it's a lot more in line with what we've know and love and expect as far as like entering things into calculators, right? The browser one is very the old school style where kind of you work inside out. But nowadays, we're just so used to these new modern calculators that have us moving from left to right, right? That you type things in the order that you see them from left to right. And so even for the final exam, you may find that the $10 is worth maybe the extra points that you would get on the final exam or your future quizzes and whatnot. So they're not expensive. There's a link on the syllabus to like Amazon, and seriously, it's $15 or less.
Thank you so much.
Yeah, of course. All right, guys, take care. And hopefully I see some of you tomorrow in office hours.